So I think we have had a pretty good introduction by Dave, who took us into a world where we already have IPv6. And I'm not going to talk about anything that could be called transition. I'm just assuming we have IPv6 in this talk. And we get there, it will take us a couple of years. But I want to talk about what happens when we have that and when we build the Internet of Things on top of that. So I will give you a pretty quick tour through the standardization in this area. Quick means I have about 30 seconds per slide. But of course, you can slow me down if that's too fast. So the background, of course, that's the canonical Ericsson Internet of Things slide here. The background, of course, is that we have been connecting places originally by laying wires to places. Then we started connecting people by giving them mobile phones. And that immediately increased the number of endpoints. And what we are now doing is connecting things, and that will increase the number of endpoints some more. And Ericsson is throwing around the number 50 billion. Cisco, I think, has number 31 billion. These numbers sound impressive. They're actually extremely boring if you think 50 billion means 7 devices per person. I mean, who of you has less than 7 devices on you at this point in time? Yeah, it probably will go well beyond that. But for now, it's a nice milestone we can talk about. So we have to scale things up. That's interesting news for the people who run networks. But when I talk to them, they just give me a blank stare and ask, what's the problem? We can do that, no problem. So that's done, I'm assuming. The interesting other point is, who's going to pay for these 50 billion or 500 billion or whatever nodes? So you actually have to scale down the nodes to make this a reality. And that's maybe the most important point here. I mean, these are the nodes that we are talking about. This is the Canadian cent here, by the way. And this is the kind of node that will be very common. And it will be in kind of everything that has a good reason to have power, have a battery. So we have to make sure that these little things actually can be meaningful citizens in the internet. And to enable people to pay for them, we have to reduce their cost. And much of the cost of these devices comes from complexity. So in the end, we have to work on reducing complexity. And that's a really new thing for people who work on the internet. So far, we just have put layer on layer on layer on layer on layer, and things have become ever more complicated. And we now suddenly have to look back and say, how much of all this stuff do we need? What can we get rid of? So this is really what the standardization activity in this area is about, managing complexity. And you have to relearn a couple of terms you may have forgotten. There actually is a monetary unit called cent. And that's very important for describing these kinds of systems. These are the 50-cent systems. It's not the $100 systems that you are used to today. It's about cents. It's about kilobytes. I have students who don't know what a kilobyte is. They think the smallest unit is a megabyte. And it's about megahertz. It's not about gigahertz. So we have to be modest in the requirements that we actually put on these systems. So we actually tried to come up with a terminology for the devices that we are targeting. And we have defined a number of classes. Class 0 is kind of the class that is too small to be a meaningful citizen on the internet. Class 1 has about 10 kilobytes of data, of RAM, and about 100 kilobytes of code space. So that would be a quite constrained node. You cannot run Unix on that thing, and you really have to run a very special operating system with some highly optimized code. But you can get very cheap chips that already have all the connections on them, so you can build cheap systems. And then there is maybe a second class, the class 2, which has half to 1 order of magnitude more, in particular more RAM, which is really a big point here, and also more code space so you can run more complex things on it. So when you talk to a meter manufacturer, they're probably going to think in terms of class 2 systems. But we will have a lot of systems that really want to be cheap and need to work with those class 1 systems. And the important thing, these classes are not moving the way we are used to with Moore's law. Because all the wonderful things we get from Moore's law get put into energy usage, lower energy usage, and lower cost. So these classes actually have been pretty much constant for the last 9 years. So since about 2004, if you just look back chip families, these classes are kind of immobile. It's now moving up a little bit. And we are getting 32-bit CPUs. So that's really a help in engineering these systems. But the classes kind of remain constant. And that's very, very surprising for people who come from larger systems. Okay, so this is what we call a constrained node. Of course, everything is constrained. We don't have unconstrained energy or power or whatever. But when we say constrained, we really mean as constrained as this stuff here. Now this should be advancing a slide. Yeah. So just for people who are old enough, this is approximately the processing power that we are talking about here. This is a PDP 1134. Yeah, they're 40 years ago, or 35 years ago, and this goes in there. So those people who have tried to run the internet on one of these machines know that it was difficult. It was not something that could be taken for granted. The next problem is those constrained nodes also bring constraints with them that have an influence on the network. So the nodes need to sleep a lot. They get networks that get on the order of 100 kilobits per second, but this is not 100 kilobits per second on an Ethernet. This is 100 kilobits per second on a very lossy radio link where you never know whether your next packet will go through. There are some physical layer packet size limits. So this is a very different environment, and you cannot take your existing application programmer knowledge for granted here. There are several radios that have these characteristics. The Zigbee radio, 802.15.4, Bluetooth Smart. I'm not talking about Bluetooth, I'm talking about Bluetooth Smart, Bluetooth Low Energy, Z-Wave, and the DECT Ultra Low Energy that is coming out now and will be in just about every home gateway within a couple of years. So these are the networks that we are working for, and the whole thing could be called constrained node networks because it's really about running networks that contain mostly constrained nodes and maybe one or two more powerful gateways. There are lots of terms for these things: Internet of Things, wireless embedded internet, low power, lossy networks, if you're really focusing on the networking aspect, IP smart objects. So I'm not going to take a side here. Internet of Things seems to be the term that is winning, but it's also the least focused one. So some people think a Raspberry Pi is part of the Internet of Things, and I don't quite know how to refute that. I mean, it's certainly also true. But this is not the one I'm talking about here. Okay, so we have these really cheap devices, and then we come with this old clunker called IP and try to make IP run on it. Why are we doing that? The reason is that IP gives us a way to integrate things. So yesterday we have seen all those silos, LONWorks, and the BACnet and whatever. And IP really is the integration protocol for this. It really makes it possible to put things together. And you have seen I've already talked about 4 different radio technologies that will be in your homes before too long. So we really need IP to make this happen. And where do we make it happen? Of course, in the IETF. So I will talk about IETF activities in this constrained node network cluster. There are 6 working groups in the IETF that are in this cluster. I have 5 of those on the slide. Xavi will talk about the 6th one later on. And they are nicely organized in layers. So we have one working group which is doing the internet area, talking about adaptation layers, IP over foo. We have one working group doing the routing. We have one working group doing the application protocol. And there is a very new working group which is optimizing existing security protocols so they work better in the constrained space. And then there is a fifth working group that essentially just generates informational documents that explain how you can implement all this, because it's new to many internet developers, and it is a good idea to have documents that describe this. Now the IETF has some 100 working groups, and some of these actually actively help us. So for instance, the TLS working group is actively looking at the requirements from the constrained node network space. So I will run through those first three working groups because I don't really have time to talk about security, and discuss what we have done, starting with the network. So the network is this 6-LowPAN working group. Oh, I forgot to mention that the 6-LowPAN working group is just undergoing a name change, which in the IETF is done by closing down the old working group and opening the new working group, because the old one was focused on wireless personal area networks, 802.15.4, and we want to signal that we are open to all kinds of radios. But the technology is usually just called 6-LowPAN by the people who are working on it. So I haven't seen anybody show this picture, so I thought I could show it here. This is when the last IPv4 addresses were distributed, and somehow the people on this picture look really happy. Do you notice that? So IPv4 is gone, and we want to use IPv6. So when we defined the IP over foo standard for 802.50.4, we didn't even start defining how to map IPv4 on it. So it's IPv6 only. 802.15.4 is a radio that was originally defined by IEEE in 2003, has undergone a number of revisions. The most likely version you will find in a chip today is that from 2006. It's marketed as Zigbee, but Zigbee is not just the radio, it's a whole silo. We're not interested in silos, so we're not calling it Zigbee, although Zigbee by now has picked up our specification, and it's part of what it's called Zigbee IP. So a typical number for this radio, it's a 1 milliwatt radio. There are versions in the sub-gigahertz and the 2.4 gigahertz bands. The sub-gigahertz is different between regions. I've only put 2 regions here. There are even other regions. And the 2.4 gigahertz region, of course, is worldwide. And this is an 802 network, but it's not Ethernet. It really doesn't feel like Ethernet. It has 127 byte packets, multicast works radio range only. So a lot of work was needed to make IP work on that, make IPv6 work on that. Well, first of all, you have to do boring things like basic encapsulation, define how exactly you find the IPv6 packet in the radio packet. Then you have to do fragmentation, because the minimum MTU, the minimum maximum transmission unit of IPv6 is 1280 bytes. Then we put in some stuff that is read on this slide, which I'll explain how we have replaced that since 2007. And I think the great idea here was to say 802.15.4 is a nice Mac. It has a lot of functionality, but we are not going to use very much of that because we are trying to stay independent of the Mac. That's why this standard 4944 actually applies so well to the other radios as well. So that actually was already approved in 2007, and people have started building systems on it. For instance, the ISA 100 system, which is used by what used to be called the Instrument Society of America, but which is now a worldwide organization, that uses this standard. So at some point we decided the header compression that was in the original document was not really good enough. You can do header compression in a stateless way, which means you only exploit the redundancy within one packet. But there is not that much redundancy there, so it's not giving you as much of a gain. Traditional header compression, like robust header compression and so on, is flow-based. But we don't have a flow of temperature readings that could be meaningfully identified on a router within a local 6LoWPAN. So we invented something new, which is based on a piece of global context state for an area that is distributed in the area, and that helps the nodes compress the 40-byte header down to something between 2 and 7 bytes. So the IPv6 headers are not big for us because we just compress them down to something much more manageable. Oh, the picture just shows your garden variety installation in a home or in an office where you have a backbone link and might even have a gateway out to something else. But don't take this gateway here. We don't have gateways in this world. Yes, good point. We have to fix this slide. Okay, third item. You all know about neighbor discovery. Neighbor discovery is a great protocol on a network that has multicast, but it turns out multicast is difficult in these constrained networks because lots of nodes are sleeping and they're just not hearing what the other guy is saying. So we had to rethink neighbor discovery a little bit and came up with something that is called 6LoWPAN ND, which doesn't use multicast at all except in the initial discovery of a router. I mean, somehow on a network you have to find out who you are adjacent to. But from that, we take it using unicast messages. So in the neighbor solicitation, neighbor advertisement messages, we have an address registration option, and a node registers, a host registers to its nearest router using the address registration option. So the initiative is inverted. It's not like the router seeking out the host, because the host will be sleeping and not hearing the request. The host, when it's awake, talks to the router, here I am, and I will stay here, please remember me. So this is really the big change. And that's actually interesting because even in Ethernet, that makes sense. So there is now an activity called efficient ND to port over this optimization to Ethernet environments like in a data center. The other thing that 6LoWPAN ND does is distributing the context information that the header compression uses. So when a host comes up in a 6LoWPAN, it gets the information that allows it to efficiently compress the packets. So we have put this right here, so we don't need another protocol. So this is what we now have. 6LoWPAN essentially is RFC 4944 from 2007 with a couple of deprecated parts, plus the new document for 6LoWPAN header compression and the 6LoWPAN neighbor discovery. And that's a solid basis to work forward on the host router interface side. And that's what we call 6LoWPAN. Now, that is actively being used, and just as an example, there recently was an ETSI plug test for 6LoWPAN. Other organizations are running interoperability events. For instance, IPSO has been running them, ZigBee IP has been running them, and so on. And of course, ISO 100 has been running their version of 6LoWPAN for a long time. So this is out there, and people working with these radios know what's it about. As I said, we have other radios, and we are now in the process of writing up the specs for that. Bluetooth Low Energy is essentially done. We are just waiting for a channel assignment from the Bluetooth SIG. They are always a little bit difficult to work with. because well, it's their specification, and if somebody comes and says, hey, we have this little piece, just put it in, they start thinking, should they have done it by themselves and so on. So this takes some time, but the document is there. Z-Wave actually has its own radio, like Zigbee has 802.15.4. Z-Wave has G9959. That's an ITU standard. So Z-Wave chose ITU for standardization. Bluetooth has its own standards organization. Z-Wave chose ITU. ULE is done in ETSI, like the rest of DECT. We're doing a lot of standards organization shopping here. But there is now a document that defines how to do 6-LoWPAN on Z-Wave, on the G9959 radio. That's nearly complete. It is scheduled to become a working document in a couple of weeks. And finally, the DECT ultra-low energy is interesting because there is a DECT chip in just about any residential gateway these days, and the newer DECT chips will have that. So it's something that should, a gateway for which should come at zero cost with newer home gateways. Now this will probably take a couple more months because DECT ULE itself is still in the process of being finalized.
Any thought about cognitive radios for this?
The question was cognitive radios. Well, do a standard and we will interface to it. Yeah, so this is not supposed to be an exhaustive list. This will go on. For instance, there is a wired standard as well, MSTP, which is based on RS485, part of BACnet, and we are interfacing that as well. And it's going to go on whenever there is anything that is useful in this space, we will interface to it. So as I said, there is a new working group called 6-Low, which is doing all this standardization. We just had our first working group meeting last week. And yeah, there are other IETF working groups that may not tell you very much that we are working closely with. Okay, so this is the internet area. I'm not a routing guy, so I'm going to make the routing part short here. There is a routing protocol for this space. That doesn't mean you cannot use RIP if you want. I mean, there are actually deployments of 6-LoWPAN with RIP, that people do that. But it's not exactly optimized for that. And the RPL protocol is optimized for this space, in particular for networks that take a mostly tree-shaped form. It's actually not a tree, it's a directed acyclic graph, so you can have multiple parents. But the idea is that many networks are just rooted in something that provides the external connectivity, and it just makes a lot of sense to organize a network around this root. RPL exists in 4 modes, 2 of which are entirely theoretical. There is a storing mode, where essentially every router keeps a map of its subtree. That is implemented in all the research implementations of RPL. And there is a non-storing mode, where you really can use class 1 nodes as routers because they don't have to keep all that state. And that's implemented in the industry implementations. We have a little bit of a disconnect here right now and have to work on that. But it's pretty clear that non-storing is going to be the mode that is used in most environments that work with really constrained devices because it minimizes the state everywhere except at the root at the cost of slightly more inefficient internal packet transport. So there's lots of stuff coming with RPL, like the expected transmission metric and so on. There's lots of good stuff here. And this has been moving things forward a lot. So RPL is based on the route over concept. Route over means that really all the devices that have a routing role in the constrained network are layer 3 routers. You can do the same thing at layer 2. You can run a layer 2 mesh network and use that. That is usually called mesh under. And there are always battles between the mesh under and the route over groups. The advantage of route over is that you actually can combine several technologies into one network. And with all these technologies out there, and Powerline, I haven't even started explaining all of them, it really makes sense to be able to put them into one network without having to make boundaries where the technology boundaries happen to be. So if your smoke detector is wired and talking to something else, so why would you have to leave the network and enter the network again and so on? So that's why route over is the concept that we are currently focusing on. But that doesn't mean mesh under is dead. Mesh under can be very, very efficient when it's tailored to a specific radio technology. Okay, so that was a very quick run through the network layer. Let's talk about the application layer some more. Now, again, this is about scaling. And when we were starting to think about scaling, we thought about what is really the application that scales well. And of course, many applications scale well, but the web is kind of the poster child here. And the web also is quite similar to what you actually do in an Internet of Things, because you are requesting information from a node, and that's pretty much what the web does as well. So the web actually has three components. HTML, now that's actually not so useful for us. We have to work on new data formats because thermostat is not going to read the HTML page of a temp sensor. That doesn't make sense. We have URIs. URIs just work in our environment. And we have HTTP. Now, HTTP is the universal protocol. It has almost replaced IP. We are working on turning that back a little bit. So when people look at this traditional stack, this is the Internet protocol stack, they look at what we have. Well, we have lots of media. We have two network protocols, IPv4 and IPv6. We have essentially two transport protocols, even though there are a couple more to choose from, and SCTP is getting some love recently. And on the application side, well, we have HTTP. So now if you look more closely, what's interesting about HTTP is not the actual protocol. That is rather chatty. Your typical HTTP request is some 500 or 700 bytes, and you don't want to spend 4 or 5 6LoWPAN packets to move an HTTP packet. But what you really want is REST, which is the underlying model behind HTTP. So we have HTTP in mind, but we are not using HTTP, but we are using a tailored protocol. So sometimes people ask us, why didn't we use compressed HTTP? Now the reason is you can compress HTTP very well, but you get all the bugs of HTTP plus the overhead of compression. So the amount of complexity you need to make this run just doesn't work very well in a constrained environment. It's going to cost a lot of battery, takes a lot of code, generates a lot of interoperability problems. So what we instead did was look at the objectives again and then do this kind of thing here. And the result was the constrained application protocol. This is essentially HTTP, but based on a 4-byte UDP header and not on a chatty text-based protocol. So it gives you get, put, delete, post, the things that you know from HTTP, but it doesn't use all the complexity of HTTP. It doesn't even use TCP. Implementing TCP also is already a significant complexity. So we go right on top of UDP and then DTLS for security, because we need security. There's the 4-byte header, and we have one addition to HTTP. There has been a lot of discussion in the HTTP camp about how to get events from a server to a client. And there are various ways of doing this, long polls and server events and so on. We have a very simple notification architecture to do that that is called observe. So you can send one request and get a number of responses in sequence with the newest state. You would use that to read a temperature sensor. It will send you a new message for every change in the temperature. So working with CoAP really feels like working with HTTP, because you have to be a little bit cognizant of the limitations. You shouldn't do video over this. It's really for small pieces of data. If you do video, your system is probably complex enough that you can run HTTP, so go ahead doing that. But for small pieces of information, like the ones that we use in constrained nodes, that's exactly the protocol that you want to have. So here's a little bit, in the IETF we like these diagrams, as you know, and this is a request and a response. So this is the 4-byte header, 2 options for the authority and the path. This is the response, again a 4-byte header, and some information, in this case the content format, and the actual payload. Okay, so this is CoAP, and the point really is CoAP is an instance of REST, so it mixes well with HTTP. You can build architectures like this one here, where you have HTTP in the unconstrained internet side and have proxies that talk to constrained nodes, all the while maybe talking to a server in the internet using CoAP directly. So they just mix and match. They're very easy to proxy to each other, and this is what will enable the web of things. Yeah, so here's an example. If we have an HTTP client, such as a cloud service talking to a CoAP server, it might ask for a light value and get that. And the next time it does an HTTP GET, the proxy might still be caching a valid value, so there isn't even a need to wake up and consume battery on the device. Okay, so there are various documents to look at. One is RFC, one is done, but is waiting for 2 security standards to finish, which will happen within this month, most likely. And 2 are in the process of working group last call or processing of working group last call comments. So this is the application protocol. What about data formats? Yes, we can ship around XML or JSON. In many applications, that's exactly what you want to do. In other applications, it may be a good idea to have a binary format. And we have heard about XC yesterday. So XC is a binary format of XML, which works well when you have a schema, when both sides know exactly what the structure is going to be. On the other hand, we often now do things JSON-based in the web, which is we don't rely on a schema, we just send the data, and there are certain reasons for doing that. And up to a couple of weeks, we had a little bit of hole here, because we didn't have a binary JSON. So yeah, we worked on that. Don't have time to go into much more detail, RFC 7049. And yeah, this is a table out of RFC 7049, and you can see it's not compressed, but it's still compact compared with other formats. So I think we have filled this corner a little bit. Security always has to be last. So this is my last slide. But security is not optional at all. So it doesn't make sense to build an Internet of Things with devices that can be taken over by someone who just has fun and switches off all lights in Asia or something like that. So we need a security architecture here that actually works. HTTP has its TLS. We know how to do this. And What we use the datagram version of TLS, DTLS, but not necessarily exactly in the same way that it's used in the web. So this is not about PKI and CAs. There are some new security processing models that we are working on. But talking about technology, this is all based on ECC now. We have the NIST P256 curve as mandatory to implement. So this is true 128-bit security. So when we talk about RSA, 128-bit security means 3072-bit RSA keys. And the internet isn't there yet. It's just transitioning from 2024 to 2048. So what we are working on right now is doing the processing models like authorization formats, commissioning models, and the performance fixes in DICE that I mentioned. Okay, questions?
I was noticing in your constrained nodes back about 10 years ago when I was doing a lot of hardware, the new Xilinx chipsets, which give you a large amount of intellectual property, so you could actually put some of the controllers in firmware to remove your software, hardware, your software issues. Are you looking at a much greater integration into the hardware level to get the performance that you're looking for at the power and cost constraints?
Well, that might come at some point. Right now, people are still writing software for ARM processors and things like that. But one of the reasons CoAP has this simple header is that in theory, it would be possible to put it into an FPGA or other hardware implementation.
Yeah, well, we were doing that looking at putting the entire IP protocol stack, or as much of that as we could, into the firmware, especially when you're talking about tactical radio systems and low power.
Yeah, I think you've implied the answer to this a couple of times, but what about denial of service amplification attacks? I'm just worried about a protocol based on UDP, that people can send a response, apply, request, and get a large response.
Yeah, we have a security consideration section, and that, of course, discusses this a lot. If we are using DTLS, we're covered. And we are usually doing unencrypted information during discovery. And there are mechanisms that limit the amount of amplification you get during discovery.
So I have a question around Zigbee IP. They just recently, I guess I don't know if it's recently, but maybe 6 months ago or something like that, they introduced Zigbee IP. Can you explain a little bit more about that, what the motivations were? And that was one big silo. Are there other silos on the networking layer that are perhaps going to be slowly transitioning to IP?
Well, Zigbee IP actually transitioned rather rapidly to IP. So the Zigbee IP stack is pretty much the stack I described here. The background is the Smart Energy Profile 2.0, which is an application layer thing, mostly for class 2 devices. So it's using HTTP and XML and so on and so on. And the industry essentially said, we have to do this based on IP or people will not buy it. So they really took in the standards that we have and built a whole stack based on 6LoWPAN, Ripple, and so on. Just the application layer is slightly different because Smart Energy is composed of slightly more expensive nodes. A meter is not a 50-cent device yet.
So they moved because their customers were telling them, we want to go to IP. Who else is left? Zigbee was a big one. Who else is in the way of moving to a completely IP-based Internet of Things? I mean,
well, I think just what everybody now runs dual strategy, a dual stack strategy. So they all have IP, but of course the old protocol doesn't go away, and the old Zigbee stacks. Zigbee is not one stack; it's a brand for a number of specifications which are all different. But the old stacks are not going away, so they can still sell.
There's new stack. You're saying they all have new stacks, new IP stacks, and they all conform to the
Well, more or less, they're all working on that. So, for instance, on the Z-Wave work. Z-Wave is a really nicely integrated standard, but even they are working on making IP available on their radio. So I think that's really the trend, adding IP as another option, but not killing your existing product line, because that would be suicide.
For now, yeah.
Okay, we got one more question.
So I'm curious on when do you think Moore's law will catch up? So we've talked a lot about, you talk about constrained nodes. A typical Zigbee chip right now has 128 kilobytes of flash already. By next year, all those things will be a lot more affordable. I know there's always a new way of doing things, but a lot of times technology catches up. So,
yes.
So to me, it looks like 10 megabit to 100 megabit Ethernet to a gigabit Ethernet, and that is better than reinventing the wheel and let Moore's law do its job. What do you think?
Yeah, as I said, Moore's law works in our space, but in a slightly different ways, because it goes into cost and energy usage. And one thing that might have been unforeseen 10 years ago is that we are seeing a lot of more Wi-Fi in this space. And Wi-Fi together with quite powerful nodes. So those people who say a Raspberry Pi is Internet of Things, those are actively using Moore's law. But again, for a light switch or the things that you will have 200 of in your home, I don't think that's a viable approach. It's much better to get the cost savings down into very inexpensive systems. And that's what we are working on.